Nonglare glass. When viewing a piece of art that is behind glass, one often is affected by the light that is reflected off the front of the glass. This is called glare, which can make it difficult to see the art clearly. One solution is to coat the outer surface of the glass with a film to cancel part of the glare. Part A, if the glass has a refractive index of n sub g equals 1.62 and you use titanium oxide which has an index of refraction of n sub t equals 2.62 as the coating, what is the minimum film thickness that will cancel light of wavelength lambda equals 505 nanometers? And part B, if this coating is too thin to stand up to wear, what other thicknesses would also work? Now, for light uh, incident on the air titanium oxide interface close to normal incidence, because the index of refraction of the air medium is 1, titanium oxide is 2.62, it's greater. For the reflected light of this surface, we're going to get a phase shift. The amount of phase shift will be equal to pi radians. Now, as for the light that enters the titanium oxide and reflects off the titanium oxide glass interface, we're going to have a the light traveling from a high index of refraction medium to a low index of refraction medium. The index of refraction was 2.62 for titanium oxide, 1.62 for silicon oxide. So there will be no phase shift during this reflection process. So delta phi will be equal to 0. But there is a path difference that is developing between these two rays, R1 and R2, and that path difference is due to the light, the time the light spends inside the titanium oxide medium, traveling a thickness T and T on the way back. So for close to normal incidence, approximately, there is a path difference of 2T, twice the thickness of the titanium oxide layer developing at this medium. So the total phase difference that we have to calculate, we need to know the equivalent of phase difference for the path difference of 2t. Now we have an equation, the phase difference delta divided by 2 pi is equal to the path difference delta L divided by lambda. So a phase difference of 2 pi corresponds to a path difference of lambda, which tells us that the phase difference that will develop due to this path difference will be equal to 2 pi over lambda, 2 pi over lambda times the path difference, which is 2t. So the total phase difference that develops between the rays 1 and 2 will be equal to pi due to the reflection from a low index to high index of refraction interface. And then we have 2 pi over lambda, but lambda in which medium? Lambda inside the titanium oxide medium, multiplied by the path difference 2t. All right, so this will give us a phase difference of pi parentheses 1 plus 4t, 4 times the thickness of the titanium oxide, divided by the wavelength in titanium oxide, lambda titanium oxide. So what should this be equal to for distractive interference? We will look for a phase difference of pi, 3 pi, 5 pi, etc. So this is going to be equal to pi times 2n plus 1, and n is an integer, which can take values 1, 2, 3, etc. That's the condition for destructive interference. Okay, so we can solve for the minimum thickness by setting n is equal to 1. So if n is equal to 1, we're going to get the path difference becoming 2 plus 1, 3 pi. So this will be 3 is equal to, because the pi's will cancel, 1 plus 4 times the minimum thickness of the titanium oxide layer divided by the wavelength in titanium oxide, which is found by dividing the wavelength in air with the index of refraction of titanium oxide. So that will give us a minimum thickness, T minimum, so 3 minus 1 is 2. 2 will make this 4, 2. So we will have lambda over nt is equal to 2t. So lambda over 2nt is equal to t. So it will be lambda divided by 2 times the index of refraction of the titanium oxide layer. So if we substitute the numbers, we will obtain for the minimum thickness, T minimum is equal to, for the wavelength in air, 505 nanometers divided by twice the index of refraction, 2.62. This will give us a minimum thickness of 96.4 nanometers. In part B, remember that it was suggested this thickness could be too low for wear out, so we might want to try higher thicknesses. So in that case, we will have 4t n sub t divided by lambda is equal to 2n plus 1 minus 1, 2n. Okay, so this was for n equals 1, 3. It's actually 2n plus 1, and 1's will cancel. So I will have 2n is equal to 4t and t divided by lambda. And this will give us the thicknesses that will result in destructive interference. T is equal to n divided by 2, n is the integer, lambda divided by the index of refraction of the titanium. So these are the thicknesses. Now, if I substitute n is equal to 1, 2, 3, etc., I can find these allowed thicknesses to be 96.4 nanometers. That's the minimum thickness I calculated in part A. Then I would have 192 nanometers. Then I would have 289 nanometers, 386 nanometers, etc. So these would be the other thicknesses that would satisfy the destructive interference condition. Okay, so in this problem, we're looking at a piece of art, and there is the issue of glare at the air glass interface. So our solution is to put a thin layer of titanium oxide coating on top of the glass in order to ensure that we will get destructive interference for the reflected light out of the titanium oxide air and titanium oxide glass interface, so they will cancel out and the glare problem will be solved. Now for the ray that reflects off the titanium oxide, we have a phase shift of pi radians. For the ray that reflects off the titanium oxide glass interface, we have no phase shift, but there is a path difference approximately equal to 2t for close to normal incidence. So the phase shift of pi plus the path difference 2t will cause a total phase difference between these two rays when they meet at this interface. Now, a phase difference of 2 pi corresponds to a path difference of 1 wavelength. So with that, the equivalent phase difference equivalent of this path difference is 2 pi over lambda delta L. So the total phase difference will be equal to pi plus 2 pi over lambda times delta L, which is 2t, twice the thickness of titanium oxide. And for this lambda, we have to be careful. It's the wavelength inside the titanium oxide, which is equal to the wavelength in air divided by the index of refraction of titanium oxide. So this must be equal to uh, pi, 3 pi, 5 pi, etc. for destructive interference. It would be 2 pi, 4 pi for constructive interference, remember. Okay, so this should be, for n equals 1, we're going to get 3 pi. For n equals 2, we're going to get 5 pi, etc. And for the minimum thickness, we're going to set n is equal to 1. What happens if n is equal to 0? You would get 0 for your answer here, you can see. So that doesn't work. So answer has to start from 1. So setting n equals 1, we have 3 pi is equal to pi times 1 plus 4t over lambda in titanium oxide. Pi's cancel. We obtain 3 equals 1 plus 4t minimum divided by lambda in air divided by the index of refraction of titanium oxide. So this gives us a minimum thickness of, here we have lambda over nt divided by 2, so it's lambda over 2 nt. This gives us, for 505 nanometers wavelength, 96.4 nanometers. Now for the other thicknesses, we can substitute pi times 2n plus 1, pi's cancel, so we obtain 2n is equal to 4t minimum over lambda over nt, or 40 nt over lambda, not t minimum. We're looking for other thicknesses as well. So this gives us t is equal to n over 2 lambda over nt. So n is the integer 1, 2, 3 here. So this nt is the index of refraction in titanium oxide. So this gives us, you can see here, n equals 1, 1 over 2, n equals 2. We will have 2 over 2. N equals 3, we have 3 over 2. So we have twice 1.5 times, etc. for the allowed thicknesses. So 96.4, 192, 289, 386 nanometers, etc. All of these thicknesses will work. And one might want to use not the minimum thickness because of the wear out problem in time, as it was suggested. It may be too thin to stand up to the wear, so it may be preferable to use the higher thicknesses.